Hello. If anybody's joined already, we're just about to get started here. I'm going to give it another minute to let people log on, but welcome. All right. Welcome to this webinar on cost factors in PCBA manufacturing, hosted by Tempo Automation. The goal here is to help engineers and supply chain folks understand the key cost drivers for their designs in prototyping and in production. So let's get started. My name is Ryan Saul. I'm Senior Director of Sales Engineering at Tempo Automation. We are a primarily NPI and small volume PCBA house here in San Francisco. We do a lot of very high quality requirement work. And as a high mix business, we have a lot of exposure to a wide variety of different designs, different design elements. We get to see a lot of quotes, get to see a lot of different cost drivers. And so the goal here is to share that. And hopefully we can all be designing and manufacturing their designs. So my goal here is to be covering the basics first, the kind of stuff everybody's going to roll their eyes about, but I'm going to cover it anyway, just to make sure. And then we're going to go through fabrication, some component sourcing issues, and then finally assembly. I will be opening it up to questions towards the end. I think that oftentimes really a lot of the most interesting nitty-gritty details are brought up in questions. So please do feel free to load your questions into the chat. We should be able to load questions from LinkedIn. So please go ahead and keep in mind that I will be answering questions when we get to the end. Okay, so what does that mean by the basics? Obviously, it should go without saying that the number of boards you are getting manufactured is going to impact the cost, along with how big are those boards. It comes together to form a fundamental question of how much fabrication material is required. So for example, if you have 100 boards, but your boards are only 1/2 inch by 1/2 inch, then that might all fit on one fab panel. But if you have 100 boards and each board is 10 inches across by 10 inches high, then all of a sudden we're talking about a lot of different fab panels that need to go into your assembly eventually. So definitely how many and how big are critical cost drivers. I know, again, this is the basics. One thing that a lot of our customer engineers don't think about is maximizing fab panel space, which is to say that most fabrication panels are 18 inches by 24 inches. And depending on how standard your design is, it's actually very, very likely that your design will take up at a minimum an entire fab panel. So ordering quantity 1, ordering quantity 5, you're paying for the entire panel. So it's important to sort of do a little geometry in your brain, figure out how many of your boards can you do you think will fit in one fab panel? And if you don't know the answer to that question, I highly recommend just asking your CM. It can be a huge cost saver, particularly on the unit cost side, to optimize for fab panel space. It's also, of course, critical how urgently do you need these boards built? It's an entirely different class of EMS service to turn something quickly. And so it's It's a there are businesses like Tempo that tend to focus on quick turn work, and there are businesses that don't even touch quick turn work. They're looking for the lowest possible cost. And so determining how quickly you need your boards is in many cases going to choose your fabricators, choose your assembly houses for you, or at least make big suggestions about who you should be using for your suppliers. Even within a supplier, as I'm sure anybody who's had boards manufactured in the past will know, there's often a sliding scale of cost associated with urgency. So I would keep in mind that if cost is no object, you can often pay suppliers to work, over the weekend or overnight or expedite, and I would say that that's often not a great idea because you're paying people to rush, and that potentially can add quality risk. But it's also going to dramatically increase the unit cost of your design. So if you can get a little bit ahead of things, understand your intended urgency, and quote for a supplier that is well suited for that urgency, it will often dramatically drive down your cost. Okay, so just to be quick, I know I said I'd answer questions at the end. We did have a question, and I don't have this written down on the screen. I think it's written down in a couple of slides, but generally speaking, the most common fab panel size is 18 by 24 inches. So that means that your design is going to fit in there one way or another. If you have a design bigger than 18 by 24, you are already dramatically restricting the fabricators that could even build it. But within that 18 by 24, there's a considerable amount of space that's unusable by you, the engineer or the ordering supply chain professional, because there might be space that's required for coupons for the fabricator to do testing, or tab spacing to allow there to be sufficient mechanical support in between individual boards in your panel. So if you don't feel comfortable estimating how many of your boards will fit in one production fab panel, I would reach out to your supplier. Oftentimes we can give you sort of some rules of thumb about how much of the fab panel is usable, and if you have a specific design already or specific dimensions, they can give you a direct answer on what quantity will fill the fab panel. All right. Okay, so that's the basics. Let's keep moving. Oh, there it was. I wrote it down. Excellent. As I said, you don't really want to be paying for expedite fees. I would say no matter what supplier you're working with, expedite fees are a very high profit margin for your CM in most cases, which is to say that this is not a good idea for you if you're trying to optimize for cost. If you avoid expedite fees, rather the best way to avoid expedite fees is to have a schedule in mind as early as possible, and to make sure that hitting that intended schedule is possible with the CMs that you are currently working with without expedite. But of course, expedite is usually available as well. Okay, let's talk about fabrication. Generally speaking, in my opinion, most fabrication cost can be attributed to one of these two buckets, which is fab technology and material choice. I'm going to get into more specifics here, but examples of fab technology, which is the technology that your fabricator will be required to apply in order to succeed with your design, would be impedance control. How fine is your minimum copper spacing? Do you have blind or buried drill pairs, and the subsequent or required sequential lamination associated with that? Are you going as far as ELIC or every layer interconnect boards? Material choice would be, is this a flex design versus a rigid design? How thick is your copper? And are you requiring a non-standard dielectric? All of these things are going to dramatically drive cost. I'm going to get a little bit more into the specifics of how much and which ones are the most dramatic. But outside of the basics, which is the size and how many, and then the urgency, these are the things that are going to most fundamentally change the cost of your design when you go to fabrication. So one of the things that is a big misconception that I think a lot of our customers have is that, I should try to reduce my layer count. I should try to reduce my number of drills. And to a certain, very linear extent, it is true that layer count and drill count do impact cost. It's an adder, but it's relatively minimal compared to a lot of the design contortions that you can get yourselves into trying to minimize these elements. So I would say, don't try too hard to reduce your layer count or to reduce your via count. Instead, work on minimizing required extra processes. So what's an extra process? An extra process would be epoxy filling your vias. Sometimes you need to do this, and this is going to be the case for all of these required processes, but epoxy filling your vias is an extra thing. It's a total sidestep in the fabrication process that would not otherwise be required. It doesn't just use additional material; it uses extra equipment and extra labor. Generally speaking, it will add to your lead time as well as cost. And so, when you're deciding whether or not to include this, what you want to do is decide whether it's necessary. And oftentimes, this is going to be a refrain for me here. We get into cost that's added by boilerplate drawing notes, meaning you might be in an organization where a significant percentage of your fab and assembly drawings are already created, and you're just editing them for each new design. This is one you should make sure not to include on designs that do not require filled vias. So what designs require filled vias? Designs that have via in pad, meaning you are drilling your vias into solderable surfaces that will require components added to them. Well, that's fair. Then epoxy filling and plating over those vias absolutely makes sense. It may even save costs on the back end. But if you don't have this, you just have bog standard, dog bone style vias on your signals, then don't do this. It's a waste of money. Additional examples of extra processes or processes that may be additional non-required fab process would be back drilling. It's another process. Controlled depth milling or a chamfer. Laser drilling is another example of this. If you need it, you should use it. But if you don't need it, you should remove it, because this is the kind of thing that's going to significantly increase the cost of your fab more than basics like number of layers or via count, etc. Next we have minimizing the use of non-standard materials. So non-standard materials can be one of two things. It could be the actual dielectric material in question. So, the most standard material you could possibly use would probably be some variant of FR4. But we often will find, even within a relatively non-standard FR4 environment, customers will specify in their fab notes what FR4 variant to use. And it may be something that's super duper available, or it may not. It may be something that their previous supplier used, or that is appropriate and available for mass production overseas, but not as available here in the United States, or vice versa. And the requirement of a specific dielectric material, when for the purposes of your functional design, it does not matter, can be a huge cost driver, because you have to buy that material if it's non-stocked, which is definitely going to add cost as well as lead time. But it's not just do they have that material, it's do they have that material in the thicknesses that would be required to complete your design, with the copper weights that are attached to your design. So it could be that they have that material, but they don't have that material with 2-ounce copper, or they don't have that material with the core thickness that's required to meet your impedance targets. So allowing the fabricator flexibility to make small modifications to the dielectric is critical. What I highly recommend, and we see this on fab notes all the time, is a call out of IPC 4101/24 or /26 or /41 to call out a class of material with required minimum glass transition numbers and dielectric constant numbers. That allows fabricators who do keep a stock of materials that will meet those IPC standards to use the material they have on hand without requiring extra, potentially expensive or time-consuming material purchasing elements. I mentioned this previously, but material that's available at an overseas, large-scale production manufacturer may not be the same material that is available at an NPI shop, particularly if you're talking about manufacturing overseas versus manufacturing nationally. So I highly recommend asking your fabricator what materials are available, or is this material that I have been using previously going to be readily available? And that can often be sort of a sneaky cost driver in your quotes that you're not even aware is driving your quotes because you've used the material many times in the past. Finally, and this is related to everything I've been saying here, avoid controlled dielectric custom stack-ups. Now, I would say as an engineer, I've talked to a lot of engineers about this, it feels better to design your own stack-up in many cases. You get to do your own impedance math. You get to design your trace dimensions such that everything works out, and you're just telling the fabricator, look, build it exactly like this, and everything's going to be great. And yet, defining controlled dielectric within your fab drawing is one of the biggest cost drivers that we see because it necessitates zero flexibility on the fab side for dielectric type, dielectric thickness, and trace dimensions. That's not to say that it can't be done. Of course, it's done all the time, but hitting your precise targets that you design digitally is in most cases more expensive and time consuming than the fabricator using their experience, using their readily available material to create successful impedance targets using some flexibility. So if you can allow it, if it's not a hard requirement, I highly recommend setting control impedance targets and allowing some flexibility in dielectric as well as trace dimensions. Just let your fabricator take care of it. Have them send you an as-built stack-up for approval so that you're comfortable with what they're about to do. You can even recheck their math if you want. But you're going to save a bunch of money that way, I guarantee it. Okay, so next, avoid use of bleeding edge technology. Now, I'm not trying to say that there isn't some cool stuff that's been going on in fabrication over the last decade. Obviously, every year, smaller and smaller minimums are possible. Neater and neater equipment comes online. And as somebody who is really fascinated with and enthusiastic about emerging manufacturing technologies, I get it. Like, who wouldn't want to design a board that couldn't have been built 5 years ago? But when you're pushing the limits of what can be done, you are dramatically constraining the fabricators that could ever do your job. And even for those fabricators that technically have the capability to do your work, they are going to charge you more just to use those emerging technologies that I'm referring to. We see this most commonly with copper spacing and incredibly thin dielectric layers. IPC standards suggest that you should not have dielectric thicknesses that are smaller than 3 mil. People push that all the time, pushing that, making it more like 2.5. That's okay. Like, a lot of fabricators will bid on that. But we'll have customers come to us and they say, look, it's technically possible to do a dielectric layer that's 1.2 mil thick. And that is true. It is technically possible to do that. But there are almost no circumstances where that's a good idea. And fabricators that will quote it are going to charge you an arm and a leg for it because they know that they're going to have a lot of boards that fall out during testing. They know it's going to take a tremendously more significant amount of engineering labor and manual labor to get that job done. So if your devices that you've chosen don't require that level of copper spacing, then you should not design your board with such dielectric thickness. You should not design your board with such required dielectric minimums. The same is true for copper spacing. If you are going to try to get away with sub 2 mil copper minimums, yeah, that is achievable these days. It is something that is possible, but it is not something that's recommended. Any copper spacing beneath 5 mil is going to start impacting cost, of course, depending on your copper weight. Anything below 3 mil is going to dramatically balloon your cost. And it's particularly going to do that when you're forced off of the sort of middle tier level of capability fabricators into the science project area of fabrication. I cannot understate the criticality of not doing this. And I'm happy to answer questions on that more towards the end. Okay. Next area is, again, sort of jumping back to the top a little bit. Adding layers is not bad. I highly recommend adding layers. If you don't have enough real estate in your design to get all your signals routed, add a couple layers. You will add to your cost, but it won't add to your cost as much as pushing copper spacing, for example, would add to cost. So I would say go for it. It's also often a good idea to add layers in order to reduce extreme copper weight. What I mean by that is, if you have a design that requires a tremendous amount of current or thermal energy to go through it, and you've got these chunky 4-ounce copper layers, maybe don't do that. Maybe instead double your layer count and use 2-ounce copper, or quadruple your layer count and use 1-ounce copper and run everything in parallel. And I know this is not an appropriate solution for all designs, but in many cases, you leave your board with similar or superior current carrying capacity and thermal weight, or thermal mass rather, and it's so much easier and less expensive to fabricate. Nobody's keeping these 4-ounce copper cores around. It's very unlikely that this is material that your fabricator won't have to go out and purchase in advance. So, you can talk to a specific fabricator about it and make sure they pre-purchase the 4-ounce copper and you get a good deal on it. But even with a good deal, it's going to be more expensive than 4 layers of 1-ounce copper, certainly. And every time you take that design to a new supplier, you're going to have that same headache. So I highly recommend considering adding more layers if it solves any of your other problems. And sort of wrapping this all together, when you are designing a complicated board, you don't often have the luxury of avoiding all cost adders. It's just not a thing that you're able to do. And so what you're doing is you're making trade-offs between different cost adders. Adding layers is an example, for example, of adding a little bit of cost to avoid a lot of cost in the future. And there are lots of examples of this. I would say the headline of cost of trade-offs between cost drivers for me is usually avoid sequential lamination. If you can possibly have your board fabricated in one lamination cycle, you should do that. It's almost never worth it to decide to go to sequential lamination in order to save cost. It always adds cost. What do I mean by sequential lamination? Real quick, this is where your board has to be built up in several separate laminations. For example, if you have a buried drill pair, you will always have at least 2 lamination cycles. For example, a 8-layer board with a 2 to 7 drill pair. That means 2 to 7 will be built up as a 6-layer board. It's going to be etched, laminated, drilled, plated, just like it were a full 6-layer board. And then they're going to laminate on layers 1 and 8. They're going to etch, of course. They're going to drill again. They're going to plate again. And you're going to end up adding another week to your fabrication and potentially 2x the cost, if not more. So if you can avoid those buried drill pairs, you should do that. I know, obviously, you can't always do that if you're designing a very complicated board. But even within a sequential lamination build, reducing the number of sequential laminations is going to dramatically drive your cost down. Meaning that if you only have 1 buried drill pair and it's a 2 lamination board, that's going to be much, much less expensive. There's going to be less quality risk, and it's going to build faster than a 3 lamination cycle board. So I highly recommend avoiding sequential lamination. In contrast, laser drilling is not so bad. Laser drilling adds cost, yes, but If you can avoid sequential lamination by using blind microvias, 1 to 2, and in that 8-layer board example, 7 to 8, it's really a good solution, both because it's very fast. It doesn't care how many drills there are. There's no consumable drill bit that's going to be impacted by the number of drills you're doing. They're all going to end up being copper filled and plated flat, so they can be drilled directly into pad. They're tighter registration tolerance. The annular rings can be smaller. I'm a huge fan of laser drilling. And so if laser drilling can solve your problem, that's usually a good idea. And then finally, oftentimes we'll have engineers who are trying to make their board less expensive, avoid potential manufacturability issues. They'll add additional worse manufacturability issues. So for example, we had a customer recently they were trying to avoid epoxy filling their vias and plating them flat, which they otherwise would require, by making an unbalanced stack up, meaning adding an additional single layer on one side that would get no drills. And that is doable. You can do that, but it's much more expensive than just doing the thing they were trying to avoid. So my advice here is talk to your CM about the trade-offs that you're looking at during your design process. If you're not clear on what is more dramatically going to drive cost, risk, and lead time, particularly, then yeah, talk to your CM about it, because your CM, once you get past the yes, I can do this, I'm trying to sell you my service conversation, and it gets to what is best for both of us as customer engineer, as customer supply chain professional, and as supplier partner, you can really get into the critical details. Okay. Let's talk about components. Obviously, components are really a hot button issue in electronics manufacturing over the last 3 years, particularly. There have been huge supply chain disruptions relative to what we've expected in the last couple of decades. Just-in-time purchasing is a lot more risky, and I'm not, and none of the stuff that I'm about to say after this changes the fact that it's a truly more challenging component supply chain environment than it has been previously. We're seeing it ease a little bit, but I wouldn't say that there's an end in sight necessarily. I'm going to be talking about some of the basics of component sourcing and how that drives cost, sort of irrespective of that those general supply chain challenges. And then we're going to sort of wrap it back into the kinds of issues we're seeing really dramatically drive costs these days. So here's a basic one: excessive BOM lines. We see this a lot from college electrical engineers. Actually, is very poor efficiency on their unique components, meaning that they're not sharing passive values, and even though their design maybe only has 400 or 500 placements, it's got 200 line items on it. Whereas if you compare that to very efficiently designed bill of materials, you might see 5,000 placements with only 250 BOM lines there. So whenever you can reduce the number of BOM lines, that's going to save cost. Remember that for every unique BOM line that you purchase, they're going to purchase attrition that is going to be created during build setup, and then, of course, during manufacturing. Each BOM line creates another engineering artifact for your manufacturing team to understand and program. Each BOM line is another inspection artifact for each inspector, both automated and manual, to be able to understand and inspect against. And I highly recommend that you reduce your BOM lines if you can. Usually I'm talking about common passive elements. And in a similar fashion, procuring from multiple vendors is expensive. Not because one vendor is super good, other vendors are terrible. That's not what I'm trying to say. But you'd be surprised how quickly shipping cost adds up. If you are, particularly during NPI, this is maybe less of an issue for mass production, but if you're only spending a couple $1,000s to have your boards manufactured, it's a real shame if you're spending $350 getting things shipped to and from your suppliers from 7 different component distributors and OEMs. So if you can get everything from one spot or 2 spots or 3 spots, that'll help a lot. Another thing that we've noticed, and this shouldn't be a huge surprise to veterans, is that if you look at the total BOM cost of our customers' designs on the material side, it is typically driven by only a couple line items. The disparity between the least expensive components and the most expensive components is very dramatic. So you'll have components that are only a fraction of a penny still, and yet another part that's $10 or $25 or $100 or $3,700. And so when, before you even begin layout, understanding what the material cost of your BOM is going to look like and be characterized by is really important, particularly when you get to mass production, because your build can only get as inexpensive as your materials. And in many cases, individual component choices are going to provide the long pole in the tent on your assembly when you get to mass production. So if you've got a $5 microcontroller on your board, that could be a $2 microcontroller. During prototyping, that's not a huge difference, but during mass production, that might be an incredibly material cost difference. So I would keep in mind your target cost for your unit cost, I would say, at production, and use that to inform your component choice when you're designing your functionality. Even if you're only going to low volume production, even if you're going to hundreds, not thousands or hundreds of thousands, we often see individual components fundamentally define the bill of materials cost. I highly recommend, it's not a waste of time, to do your own tiny analysis of your bill of materials and figure out what are those line items that are driving your cost. Because sometimes you have no choice. That's just what's required to make your design work. But many times there is a choice. And if you make those changes early enough in your design process, you're not going to be stuck behind a scheduling debacle later on. So it could be, and we see this all the time. I can't count how many times this has happened with our customers. They will decide that they wish they'd used a different component well into engineering validation during NPI. And they have to stop and go back and change the component because it's either no longer available or it's more expensive now than they wanted it to be. So preparing for those situations is a good idea. And then sourcing delays add downstream costs. And I think this is, again, shouldn't be a surprise to any of you who've been in the industry, but when something is hard to source or will be driving lead time, it adds potential downstream cost to your entire build. Meaning if your material can't all be received at once and some of your material is going to have to be warehoused for weeks or months in advance, or there's confusion about when you're going to be kit clear and your whole schedule gets blown up, and then you have to pay to expedite. You're trying to recoup your schedule in manufacturing. This is a very common a solution that you can avoid if you get ahead of your sourcing on your components. So what have I been talking about specifically? Build your bill of materials for sourceability. And this is I would say novice engineers often make this mistake. They build their BOM for functionality only, and they don't really consider sourceability, and then surprise Pikachu face when it comes to sourcing their bill of materials. So I highly recommend that. As I mentioned, consider extended production quantity costs at your early design stages. Identify suitable alternates early before submitting to a manufacturer. Our most experienced and successful customers will often submit bill of materials that have multiple alternate components available already displayed on the bill of materials, so that if between the design completion and the design purchasing stage, some components go in and out of stock, that's okay. You already have alternates on your bill of materials. For those components for which there are no drop-in alternates, you got to be securing them as early as possible. So you may not even be fully baked on your design. You've just finished your schematic and your bill of materials. You're going into layout. You already know which parts you definitely need. There will be no alternates. You should already be buying them. Already buy them, or get your supplier to buy them on your behalf. I would say it's become, instead of the exception, it's become the most common scenario for us as an NPI manufacturer to be receiving hybrid consigned kits from our customers. Even when we are building full turnkey, they'll say, okay, we want you to quote this full turnkey, but FYI, these 3 line items, we're going to be providing those. We've had those, and that is such an important solution to this issue. Another issue, which is related to that last point, which I didn't write down here, and related to the overall supply chain challenges that we've seen around critical components over the last 3 years. You want to avoid going to the gray market or to brokers for your components. Obviously, there's a quality aspect of that, which I'm actually not going to talk about in this case because that's not what this discussion is about. We're talking about cost here. Component brokers are the ticket scalpers of component distribution. If you're going to a broker, you might pay 10x or 20x the price for each part. Think of how that might drive the cost of your build. If this is one of those line items that defines your material cost, you think you're paying, $2.37 per part, and all of a sudden it's $20 a part. You may have just blown up your budget right there, and that's before you consider the additional costs associated with validating that these components are acceptable coming from the gray market. So what these brokers are doing is they're buying parts, they're speculating that they're going to be maybe going obsolete. Maybe they know this, or maybe they've seen an uptick in criticality of these parts. They're buying up all the supply and then selling them out at 10 times the price. And this is a well-known, very profitable racket. You don't want to be involved in it if you possibly can avoid it. So secure your parts early. And if your parts can only be secured through the gray market, I would highly consider designing them out if you can. All right, we're motoring on. We do have a bunch of good questions already, and I will be sort of backtracking to answer some of those questions, I promise. I'll get back to you guys. I promise. I do see you there. All right, assembly. So what drives costs in assembly? I would say that as an assembly house, it's incredibly obvious to Tempo that the heart of assembly, of modern assembly, are robotically placed SMT components. If your design element is a robotically placed SMT component, you're doing it right. That's as low cost as it possibly can be. Anything that is not a robotically placed SMT component is going to incrementally add cost or dramatically, exponentially add cost, depending on what the design element is. So an example of something that is a sort of linear adder is a through-hole part. Through-hole technology is super duper mature. There's no doubt about it. It's not as much of a quality risk as some of the other items on this list, but it is going to add cost. The same exact component, if it was an SMT version, you're going to pay maybe 1/10 the cost for that one installation of a part. This is because robotic assembly is incredibly efficient, and the same is not the case for through-hole assembly. It can still be robotic soldering, but it's very unlikely to be robotic placement, which means some person is going to physically put that part in its place. The most common example we see of customers getting this wrong is with through-hole test points. There's good reasons to have through-hole parts in your board. Don't get me wrong. They are mechanically more sound. They're thermally more connected to the core of the board. It's good. It's a good job to use a through-hole part sometimes. But test points is an example where there's really very limited value in having your test points be through-hole, unless there's going to be a lot of physical grabbing and manipulation of your board by its test points. We had one customer that designed their board with more than 100 through-hole test points, and every single one of them could have been an SMT test point. And if they had made that one change, then the per board cost of their assembly would have probably dropped by 20%. And so been easier to manufacture. It would have been cheaper to buy the components. It would have been cheaper to assemble the components. There would have been fewer quality issues. It would have been a 100% win. And so I highly recommend reducing it if you can. I would say that press fit is another example of a technology that it has good applications, but should be avoided unless you need it. Anytime you have press fit, you're going to have the evil dragon of NRE rear its ugly head, and so that means that there's going to be a die that's required to press your component in. There's going to be press fit support fixtures that are going to be required to safely press into your board. And if you're building in mass production, actually that's a relatively low additional unit cost associated with that. But in prototyping, this can be a very dramatic element of your cost for fixturing. And I would say that goes for SMT and through hole as well. If you can avoid fixturing, you're cutting thousands of dollars off of your SMT and through hole pricing. So that can be huge. It's sort of a theme, I would even say. So compound complexities is a little bit vague. Sometimes easy things become hard when combined with other easy things. So an example of this would be through-hole solder joints close to SMT solder joints. If you have a easy SMT and an easy through-hole solder joint, you put them close together, and now you need a fixture. Because if you're going through full wave soldering for mass production or selective wave soldering for more of an NPI small scale build, you have to protect that SMC solder joint from the solder wave. And that either is done via a manual process, meaning some technician with a squeezy bottle of mask, or with a hard tool. And in either case, you're adding additional labor or NRE cost to your build. Another common example we see is boards that have very, very fine pitch SMT elements or thermally sensitive SMT elements. No problem. These days, fine pitch elements are easy on the assembly side for modern manufacturing equipment and processes. But they also include heavy magnetic or mechanical solder joints with high thermal mass on their board. And this is challenging because now you have to design a reflow profile that will successfully reflow these large mechanical or thermal solder joints without damaging these very sensitive components. You have to use a stencil that is thin enough to apply the solder paste minimums that you need to be successful in SMT without bridging on these micro BGAs and 0105 style packages. And yet also be thick enough for these heavier, more mechanical or thermal connections. In many cases, the only solution to that is a stepper stencil or 3D tooling, which is more expensive. So if you can avoid including these heavier elements and these super fine pitch elements on the same boards, that's ideal. Separate them into two boards and you save a tremendous amount of money, engineering time, potentially quality risk as well. And that's not even getting into the top side, bottom side issue, where if you have, this is another common, you see this with college projects particularly, you'll have physically large and heavy components on the same side as the most sensitive BGAs or QFNs that require careful thermal management, meaning that you're going to end up needing to reflow those parts upside down. It's very likely, meaning you need to either chip on them to the board or you need some sort of fixture to keep them on. So anyway, this is the kind of compound complexities that I'm talking about. Again, I highly recommend talking to your CM about what's driving cost. Okay, another example is cleaning methods. These days, the industry is moving towards use quote unquote no clean flux, but then clean the boards anyway. All of your manufacturers should be washing the boards post-assembly. It's not expensive. That said, if you have elements on your board that can't go through an inline wash process, I'm talking about pressure sensors or microelectrical, mechanical things like microphones. that would be destroyed by an aqueous process, then a standard inline cleaning solution won't work. And you either need to go for manual cleaning or no cleaning at all. And if you're okay with receiving boards with residue, that's on you. I would say that that's less and less acceptable in the industry over the last 10 years. It's a reliability concern, particularly if you're going to be doing any conformal coating. So consider sort of what pressure you're putting on the wash process when you are choosing components that would be damaged or destroyed by wash. And the solution is, in many cases, a relatively manual one, which will add significant cost. And then, of course, additional sort of assorted requirements on the inspection and testing side. Post-assembly is always going to add cost. This could be sort of functional test where you provide a test process for your manufacturer to review. It could be flying probe or ICT. I would just, consider, do you really need these things, for the stage of the build that you're on? So as I'm saying, at prototyping stages particularly, strip out unnecessary requirements that may be required for production. Again, this is where sort of boilerplate style notes can get you in trouble. You may be designing your drawing for mass production, but then don't let the NPI manufacturer know that you don't actually care about some of those elements for prototypes. You end up getting relatively expensive quotes that way. What am I talking about? I'm talking about things like staking underfill conformal coat that you probably don't want during prototyping stages, but also some cleanliness requirements. A huge offender here is ionic chromatography for cleanliness testing. If you're building 5 boards to figure out if your design works, you do not need ionic chromatography. And it's going to, in many cases, we've actually had customers where the entire cost of their build, which includes the fabrication, the components, the assembly, all the labor, is less than the additional cost of ionic chromatography. So if you require that to qualify your production at, as a sample, maybe at mass production, that's a whole nother thing. But during NPI, it's usually a waste of money. And I understand that sometimes there are FDA requirements. If you're having a medical device, that's a whole nother thing. If it's a regulatory thing, you should go for it. I know that that you don't need it, but we've decided as a society that you need it, so you're going to pay for it. But in most other cases, you should avoid that. And then in general, minimize manual processes. Anything that's in your assembly notes that is going to not be able to be accomplished on a conveyor by a robot is going to add cost. It's going to add direct cost to your quote, meaning they're going to charge you for labor, but it's also going to add quality risk and associated additional downstream cost for potential error. The consequences of manual processes are lower yields in general. Lower yields mean less certain delivery timelines, potentially expediting requirements. So anything you can do to minimize manual processes. So an example of a manual process would be what you call blue wires or some sort of necessary rework. We see this oftentimes with some of our customers that have very low flexibility in their design, meaning they're perhaps prohibited by their internal company policy to roll the rev, but they know their design is wrong. And so they just want us to build it from scratch, but then also do rework at the end. And as an engineer, it's a little bit frustrating, of course, to know, why don't you just change the copper trace, and then you don't need this wire at the end of your run. It's not just for the cleanliness of the design. You're adding a significant amount of cost at the end of your design. It's so easy from a unit cost perspective to move the copper on your fab relative to soldering additional wires on your board post-assembly. So definitely, I would minimize that if you possibly can. All right, sort of motored on through that. I feel like I was both talking too quickly and too slowly at the same time. So I'm gonna start answering some of the great questions that I see in our chat. And I appreciate you guys waiting for me to get to this stage to answer some of these questions. So from Amba, we have, does that mean materials are not equal on a brand also? So it is true. It is true that material suppliers will usually have a pretty broad catalog of different materials that they manufacture, and they are differentiated by spec in most cases. So Isola is a good example that they make a wide variety of different materials that are intentionally different. So you can't just have Isola material. You have to specify Isola 370HR or 408HR or P95 or something like that. That said, most suppliers, most material suppliers or manufacturers, I guess is what I'm really saying, will intentionally provide an equivalent material to a successfully selling material from one of their competitors. Meaning that if you have a material produced by Isola that's doing really well, that American engineers are using their designs, you're going to have Shengyi manufacture a material that is equivalent, as close to equivalent as possible in the specs, and it'll be called something else, something very different, of course, than whatever the Isola material is required or is called. So in many cases, there are 2 or 3 acceptable equivalents that have almost identical stats from a different material supplier. Where it gets trickier is when your design requirements get a lot more specific. So let's say if we're moving into the RF or high-speed area, where you have a very, very tight dielectric constant or permissivity requirements, and it can really only be solved by a specific Rogers material that's on the market. There may be a Megtron that also can satisfy your requirements, but maybe not. Maybe it's only that specific Rogers material, and in those cases, you just have to buy it. There's no flexibility there. All right. Another material question is from Chance Carpenter. At what copper thickness do things become exotic? That's a great question. So the most common copper thicknesses, and you will never add cost to your design with 1/2 ounce and 1 ounce. That's standard. All materials are manufactured with those thicknesses of copper clad. When you get to 2 ounce, it's not exotic. It's a little thick. Depending on the core thicknesses that you have in your design, it may not be automatically in stock at your fabricator at 2 ounce. It may add material lead time. It may not. Maybe they have it, particularly if your dielectric material is relatively common, like 370HR, for example. Anything above 2 ounce gets into the more exotic category. So 3 ounce, 4 ounce, I would consider that exotic. Anything above 4 ounce, I would consider extreme. So up to 4 ounce, it's reasonable. There are reasons that I would say you should have that in your design. Anything above 4 ounce, and I think a mistake has been made. Not because there are no designs that justifiably have 6 ounce copper, but those designs could probably be designed more efficiently towards cost. But it sounds like an exciting project. I mean, that's probably a lot of current that you're using. So hopefully that answers your question there. All right. Another question, a related question from Chance Carpenter. Any concerns with specifying copper weight by finished copper thickness, base thickness, and plating thickness requirements? That's actually a great idea. This is a common, it's less about cost. It's more about clarity. Oftentimes our customers will not tell us which they meant in their stack up or in their fab drawings. So it's very important to note what you intended when you're specifying copper weight, particularly if there's a little stack up diagram. It says 1 ounce on the external layers. Did you mean starting or did you mean finishing? Finishing being a post-plating process, and starting meaning that's the foil on the external layers. So specifying is a really good idea. I would say that every fabricator's plating process is a little bit different. There are IPC standards for how thick plating needs to be in order to satisfy class 2 or class 3 requirements. And in general, I would allow a little bit of flexibility there. It's not going to be exactly 1.9 mils if it's 1.5 ounce, for example. There's going to be a tolerance. So specifying starting weight and plating thickness tolerance is a good idea to see that in your fab notes. Usually for single lamination boards, internal copper layers are just whatever they are. 1 ounce copper material, it's 1 ounce copper. And external layers are where you see the significant deviation due to plating. But once you have sequential lamination and you've got plating steps internally as the board is built up to its final thickness, then starting and finished copper thicknesses are critical to specify in your design. All right. Speak to the incremental cost of dual side components from Michael Price. So it used to be the case, I would say, that having a dual-sided assembly was a significant cost driver. And it still drives cost, but it's not so bad. It's become relatively standard in assembly to have parts on both sides. So as long as you're following best practices, like, for example, put all of your most critical components on one side, put a pile of passive components on the other side, you're really not going to be adding a significant amount of cost. It's when you have that stacking or compound complexity associated with maybe putting the wrong parts on the wrong side of the board. As an assembly house, what you have to do obviously is choose which side to go first. And if you've got one side with a bunch of simple passive components, it always goes first. And then the next side, the second side, will have the challenging elements, the heavy elements, the sensitive elements. And if you are splitting your challenging elements between the two sides, that can add significant engineering cost and quality risk, and thus your quotes will be higher. All right. Next I have from Austin Pullman, is there a significant cost reduction associated with keeping all through-hole components only on one side of the PCBA in a case where SMT is on both sides? That is a fantastic question. So I would say usually yes. Usually you will save a significant amount of money by having all of your components on one side. During NPI, it is maybe less of a dramatic change because NPI solutions for through-hole are a lot more flexible. So selective wave, or if you're having your through-hole components hand soldered, it's not as driven by which side the components are added from. But in mass production, it is dramatically impacted by the number of through-hole sides because they're likely going to be going through a full wave process. Full wave process requires a wave pallet or a supporting fixture that protects the design from damage due to the wave. So if you've got two sides, you definitely need two wave pallets that take into account the 3D elements of your design during that through-hole step and protecting all of those vulnerable parts from the solder wave. It's a whole extra process. And even for NPI, it is recommended. One of the things that's often not understood by I would say people who haven't been in assembly is that components are designed to survive the process that they will be manufactured with. So what does that mean? That means that SMT parts are designed to survive the oven. These days, lead-free assembly is relatively standard. So parts are designed to survive during lead-free reflow temperatures. But they're not designed to survive in processes that they aren't expected to be used within. So an example of that is that through-hole components are usually not designed to survive an SMT reflow oven. It's too hot. They're designed to survive heating from below, soldering on their pin. And so oftentimes when you have through-hole components on both sides, you end up exposing the components on the underside, or let's say you do single side through-hole assembly, you have to flip the board over and do the second side through-hole. The selective wave, the full wave, even if you have masking or a fixture protecting those components, there's actually an incredibly intense heat transfer happening with through-hole soldering. And through-hole parts are not as thermally hardened as SMT parts most of the time, many times, particularly with connectors. So you can end up damaging components that are installed first if there's through-hole on the other side that's anywhere nearby. So I actually highly recommend against through hole on both sides unless you have to. Another related issue, this is a little bit more esoteric, but definitely can drive cost more than you'd think. Edge connectors, even if they're SMT only edge connectors, but certainly if they're SMT plus through hole, edge connectors can often add more cost than you'd think because these boards are traveling down a conveyor. That's how these robotic systems work in all cases, is they are conveyorized. And if your board needs to travel down a conveyor and you have parts that are sticking out over the edge of the board, then you are very likely going to require a fixture, particularly if these edge connectors are mid-mounted, meaning that they sit low. You see this these days quite often with USB-C connectors on layouts. They're designed to fit within a slot on the edge of the board and extend a little bit outside so that, for whatever product enclosure they're intended for, they're going to be perfectly placed. If they're mid-mounted, they cannot use the rails or the additional panel material to support them, right? They're going to sit below the surface of the board, and so there's going to need to be a fixture to support them to make sure that they don't tilt during SMT. All right. I can talk for an unlimited number of time here. I'm running up on my time. I'm going to try to answer another couple of questions here. Daryl Strode. How's it going, Daryl? Well, I haven't talked to you in some time. Good question. With BGA packages getting bigger and bigger, aside from component cost, does a larger BGA cause higher manufacturing costs? Would multiple BGAs be cheaper on the manufacturing side? The only answer to this, and it's unsatisfying, is it depends. Certainly, you can make a BGA package that is too large for some SMT equipment, and it depends on the SMT equipment that you're using. Some SMT equipment is only going to be able to accurately place components up to certain sizes. Actually, I would say all SMT equipment has certain size limits. And the same is true for pitch. Some would rather have a larger component with a wider pitch rather than a smaller component with a finer pitch. I would say, generally speaking, though, the additional cost associated with very large BGA components is on the material side. Usually we'll see these very large BGA packages. They're FPGAs. That's the part that costs $5,000 and you have no attrition. That's the part that is unobtainium. You literally cannot buy them. And so there can be no quality issues associated with these parts. And that ends up adding additional labor, both on manufacturing and on the purchasing side. All right. Adam Parent, I've always been told the number of trace layers is the biggest cost driver. Can you speak to how these costs may have gone down over the years? Yeah, definitely not the case anymore. I would say that when it was one of the most fundamental, it's still one of the most fundamental. When it was one of the biggest changes that could be made in fabrication, it was, of course, the biggest cost driver. As newer and cooler things have been developed, as new fab technology has emerged and made new design elements possible, almost every new thing is always more expensive and challenging than the old things. So that means that your design that's 10 layers, but they're trying to fit it on a sub 31 mil mechanical thickness, meaning that the dielectric layers are all smaller than 3 mil, and they're doing it with copper spacing that's it's 2 copper spacing. That is going to be so much more expensive than a 14-layer board at 62 mil thickness. It's not even funny. It's going to be 4 times more expensive, because even though it's only 10 layers, the other elements of the design have eclipsed the layer count in cost. So yeah, I would say it's the newer, cooler technologies are always more expensive, and layer count is still a cost, but not as significant. I see a question from Kobe. Another blast from the past. How are you doing, Kobe? I should know this, but I have a client. I'm going to refer to you guys. Do you have the ability to do signal integrity testing on antennas? We do. So antennas can take two varieties, or 2 broad varieties of antennas. You can have integrated antennas on the board, where the copper on the board is the antenna, in which case, of course, You can do testing on the signal integrity of that at the fab stage, post fabrication, pre-assembly, and then you have antennas that are components that would have to be analyzed post-assembly. But in the other case, that's something that Tempo can help with. All right, I'm already 5 minutes over. I've got 2 more questions. These will be the last 2 questions. I really appreciate all these excellent questions that you guys have asked. Austin Pullman, again, asking, are board cutouts / slots a cost driver? What about non-rectangular shapes? Board cutouts and slots are not a very significant cost driver. Yes, you will add some cost, but it's not super significant. That said, you can design an expensive slot if you want. So an example of this is we see a lot of newer engineers design cutouts or slots with internal right angles, meaning that like a rectangular slot, for example, which experienced engineers will know is not possible because internal slots, or all slots, are cut with rotary bits, meaning that there's a circular drill bit that's going to route out the slot. Or in some cases, in the case of a nibble route, it's going to drill multiple times and then route. And so because the bits are round, the corners are round, always. You cannot get a right angle. But if you require a very, very low diameter on that curve, on that internal slot, that might be very expensive, either because the bits are non-standard, the bits are highly consumable, as in they're likely to be destroyed by your project if you have a lot of slots to cut, or it may disqualify your fabricator. So you can definitely design expensive slots, but your average slot that you'll see on the data sheets for connectors, it's really not going to drive a significant amount of cost. And non-rectangular shapes, similar. It's not a dramatic cost driver during fabrication. I would say that it's kind of all the same on the fab side. It can drive cost because it's non-rectangular, it doesn't fit as many of your boards within one fab panel, as in more material will need to be consumed. That can definitely drive cost. Another thing to keep in mind is that during assembly, your boards still need to pass down rectangular conveyors, meaning that if you have a circular board, it can't be conveyorized. Instead, it needs to either be built in panel, which is the best solution if it's possible. So you'll have an array of 2 to actually 1 to 10 boards. You can have an array of 1. Pass down the conveyors, go through assembly, and then be routed out at the end. But if you can't have an array, let's say you've already had your boards manufactured and they're circular now, then they need to be fixtured, and that can be kind of expensive. Have a supporting fixture, extra couple $1,000 depending on how many fixtures you need for your assembly. So just keep in mind that particularly during assembly, it's all going to be conveyorized, which means it needs rectangular edges. There's no way around it. So you can usually do that with the panel or the array, but if you need fixtures, you need fixtures. Okay. And then finally, how important is the number of hole sizes? This is from Carl Muster, typical diameter tolerance for, say, 10 mil. So number of hole sizes does, to a certain extent, add cost. This is because during drilling, this is how many different drill bits are they going to need. They're gonna do the drilling in sequence. It's not a dramatic cost driver. It is a cost driver. As I mentioned when I was talking about laser drilling, mechanical drill bits, in contrast to laser drill, mechanical drill bits are consumables. So every time you're drilling anything with a mechanical bit, you're using up that bit. Some bits are really common. So 10 mil is a good example. That's a very common drill minimum. All of your suppliers are going to have just oodles of 10 mil drill capability. But mechanical drills get real small. You can get down to 5 mil in many cases for mechanical drills, if not smaller. Those drill bits are more fragile. They're less common. So if you have thousands and thousands of those drills, it's going to be a little bit more expensive, but not crazily more expensive. Another thing that I think a lot of engineers don't talk about or think about when they're designing their drill drawing is, do they mean finished thickness or do they mean drill thickness? because in most cases, fabricators will look at the drill drawing, and unless it says otherwise, they're going to assume that that means finished thickness. So that means that you want your drill to finish at 10 mil. That means that they have to drill bigger than 10 mil, and then it plates down to 10 mil because there's a minimum plating thickness in those holes to meet class 3 requirements, for example. And so they might drill it at 12 or 14 and then plate it down to 10, which is one of the reasons for annular rings, particularly wide annular rings in mechanical drilling. In many cases, individual customer drill drawings will address this issue by providing a minimum and maximum finished hole size for each drill type. So for example, we often see, let's say you've got these 6 mil minimum drills, that might be maximum 6 mil, minimum 0. And what they're saying to the fabricator is, look, you can plate this shut, I don't care. I don't want it to be larger than 6 mil because I have spacing issues, but make sure all of your tolerance is on the bottom side of the 6 mil. And it's totally acceptable to provide that kind of feedback to a fabricator. All right. Okay, thank you guys, everybody who contributed questions and for attending in general. I'm sorry for taking extra long. I expect hopefully people jumped off in order to get to their next thing if required. And if you have any follow-up questions, please do reach out to us at Tempo. I'm happy to address those questions. I'm Ryan at tempoautomation.com, and we'll get those questions answered. Have a good day.